Okay, so we're going to look at this quasi-linear PDE. It's a first order PDE, so let's solve it by the method of characteristics. So we firstly let x be a function of t, right? We now want to deduce what happens to u as a function, du as a function of t by the chain rule. Du dt plus dx dt du dx equals, so that's the rate of change of u with respect to t as a total derivative along the characteristics. So we compare with our initial PDE, and we deduce that if dx dt is equal to u, this defines a characteristic, du dt equals u. Right, that's what we would get out of this, right? This equals this, right? So those two things are equal. This equation here, number 2, is really straightforward. It's a separable first order ODE. It implies that u has exponential solutions. Right, so you do your usual separate and integrate, and you get this. We have an initial condition here, so we can apply it to find out what capital A is. So I'll just sketch in the solution here, du, in case anyone's worried. All right, so you exponentiate, you sort everything out. With the plus c becomes an a, and so on when you exponentiate. Since u x naught equals 2x. Now this is x naught on our characteristics, right? It's the x value at time t. Right, so that we've got this initial pulse thing as well. We can write 2x naught equals a, right, at t naught. So we now have a value for a, and we have that u equals 2x naught e to the t, right? So this kind of tells us how our x naughts evolve in time. Obviously, it's 0 elsewhere. That's just going to imply that a is 0 everywhere else outside of this little pulse region. So we're just going to have this pulse that evolves in space and time, and everything else is going to be 0. So this is enough information to go back and solve equation 1 for our characteristics. So dx dt equals 2x naught e to the t. All right. Now we can integrate this. It's a directly integrable equation. X naught's a constant. E to the t is e to the t when you integrate it. So we do have to deal with this constant of integration, however. But we can stick our initial condition in again. Right, x at time naught equals x naught, right? That implies x naught equals 2x naught e to the t is 1 plus b, so b equals minus x naught. And that implies x equals 2x naught e to the t minus x naught. And now, because we have our u in terms of x naught, we want to find out what happens as x evolves in time, right? Which is really following this equation here. We need to rearrange this for x naught. So implies x equals 2 e to the t minus 1 x naught equals x divided by 2 e to the t minus 1. And then u, what was it, 2x naught e to the t. 2x naught times e to the t. Right, and you can simplify this down, I guess. Cancel out the e to the t's a little bit if you wanted. Like so. That's slightly nicer, I guess. Alrighty.